Okay, I'm going to start again with this, okay, just because we've had a few late arrivals. So let me go back to this graph. This is the first slide that I used. This is a plot of the free energy of the liquid and the solid phases as a function of temperature. Today's lecture is about solidification. And at this point, the solid starts to have a lower free energy than the liquid. So solid is the stable phase in this region, and the liquid is the stable phase in this region. And at this point, which is the fusion temperature, or the melting temperature, the two phases have exactly equal free energy. Okay? And what I want to do is I want to derive the difference between the free energy of the liquid and the solid as a function of temperature. So if I look at just the fusion temperature here, then I can write the free energy change is equal to the enthalpy change times minus the fusion temperature and the entropy change, and that must be equal to 0 at this point. And therefore, I have the enthalpy of fusion as a function of the entropy of fusion and the melting temperature. And now I'm going to assume that both the enthalpy of fusion and the entropy of fusion don't change much with temperature. Okay, so we've got values for those quantities, and they don't change much with temperature. If I do that, then for the general equation describing the difference in free energy between the liquid and solid, I can simply substitute for this the enthalpy of fusion, and for this, the entropy of fusion. And this is now any temperature. Okay? So using this equation, it's straightforward to find delta G at any temperature T. And of course, we have a relationship between the enthalpy and the entropy here. So I can simply replace the entropy term by this, and therefore, I get the driving force here, delta G, as a function of the entropy of fusion and the undercooling below the melting temperature. Okay, so this is an approximation because we are assuming that the enthalpy of fusion and the entropy of fusion don't change with temperature. And it should be reasonably accurate if you're not very far away from the melting temperature. In the vast majority of solidification experiments or real scenarios in production, the undercooling will be small. Okay? Delta T will always be small. Now, why do you think the undercooling should be very small? Why doesn't, okay, so here's another question. Why doesn't solidification start the instant the system goes below the fusion temperature? You know, what is necessary before solidification can start? That's right. So we have nucleation to cope with. Nucleation involves the creation of a new surface, and that requires a certain amount of undercooling. Okay? Now, why in most solidification scenarios don't you need to have too large an undercooling to induce solidification? Heterogeneous nucleation, you're usually doing it in a container, and the walls of the container are very good nucleation sites. Okay? So delta T is going to be quite small, and therefore this approximation is reasonable. Okay, so we've got now the free energy change. We now look and we assume that nucleation is easy, so we've created a particle, and we're now looking at the movement of an interface. And what is the rate at which that interface moves? Now, of course, a solid has a different structure from a liquid. You know, in the liquid, the atoms are more or less randomly arranged, whereas in a crystalline solid, there's a long-range periodicity. So there's going to be a barrier to the transfer of an atom from the liquid to the solid. And I've drawn that barrier over here. This is the activation barrier to go from the structure of the liquid to the structure of the solid. And atoms will jump in both directions, you know, because it's always the case that, you know, there's nothing to stop an atom from going in the reverse direction. So this is the height of the activation barrier that an atom in the liquid has to overcome to get into the solid. Can somebody tell me what the height of the activation barrier for the reverse jump is? Yeah. Yeah, so it's much bigger. If we are below the fusion temperature, and delta G here is of that magnitude, then to go backwards is going to be a larger activation barrier. So we can write the velocity as a function of the forward jumps less the reverse jumps. So we write the velocity as being proportional to the chances of successful jumps in the forward direction, liquid to solid, less the jumps in the reverse direction. Here the activation barrier is larger. Okay? So we've now got a function for the velocity, the driving force, and the activation energy for the transfer of atoms across that barrier. I'm simply going to take this term as common between these two. So this is a rearrangement, velocity with this term here, which has the height of the activation barrier, and then you have 1 minus exponential of this term. And I've said to you that solidification normally happens at small undercoolings, so delta G is likely to be small. So I can actually replace this 1 minus exponential delta G over kT term by just delta G, because there's an approximation which reduces the whole of this into just delta G if delta G is small. Okay? You know, 1 minus this term becomes almost the same as delta G when delta G is small. Okay? So you can see that the velocity is proportional to the driving force, and therefore it's proportional to the undercooling, because we demonstrated that delta G varies directly with the undercooling. Okay? So it's a very simple equation to derive, and it tells you the velocity as a function of the undercooling and the activation barrier for the transfer of atoms across the solid-liquid interface. Everyone happy with that? Okay. Straightforward derivation. Now, it's straightforward because we are dealing with a pure substance. Okay? There are no solutes partitioning between the liquid and solid. We'll come to that case later. Now, this is a casting which you can see in your laboratory. It's actually an aluminum alloy, and liquid has been poured into a mold. This has solidified, and we've removed the solidified ingot. The scale of this in a laboratory experiment might be about that big. In real life, it may be huge. Okay? Many, many tons of metal. What I'd like you to notice is that there's a lot of structure in this. First of all, the scale of the microstructure near the wall is much finer than as you go away from the wall. Yeah, you can see the crystals here are much finer than here. Okay? And secondly, that as you get nearer the center, there are some grains which look equiaxed. That means they have the same dimensions in all directions, whereas the grains here are columnar grains. They are long. Okay? And thirdly, that there is this what we call a pipe. Okay? This pipe is because when the liquid freezes, there is contraction, and therefore, you know, even though you fill the mold up to here, you will end up with a hollow, and you have to cut this off, and that's a waste of material. So later on, in this series of 3 lectures, I'll show you a process which completely avoids this problem, and that is the process which is used in mass production. Completely avoids the problem of this pipe here, which comes from contraction. So let's have a look at this structure in a bit more detail. We realize that the structure near the wall of the mold is fine, it's coarser here, and that there are some equiax grains in the middle. And I'm going to draw this schematically just to make it a little bit more clear. So this is now our mold. The structure here is much finer than here. It gets coarser. And these are columnar grains. And these are what we call equiax grains. That means they are more or less the same size in all directions, forming in the middle of the liquid. Now, the reason why the grains are finer here is as soon as you pour the liquid in, you know, the mold is quite cold. And therefore, there is a large undercooling, and you get lots and lots of grains forming. Okay? Now, once they have formed, there are certain grains which can grow faster than others because there is an easy growth direction. So for example, in cubic materials with the cubic lattice, the growth rate is fastest along 100 directions. Okay? So if that is the case, that the growth rate is fastest along 100 direction, and this particular grain happens to be oriented, so that its 100 direction is parallel to the direction of heat flow, then it will grow faster and stifle the growth of all the other grains. Okay? So if I just sketch that out, so this is our mold surface. And I've nucleated several crystals, and they're all trying to grow in this direction. But this one has rapid growth, and therefore it stifles the growth of the other grains. Okay? So this is oriented so that its 100 direction is more or less parallel to the direction of heat flow. So in that way, you get a coarsening of microstructure as you go away from the surface of the mold. And the reason why we get grains which are equiaxed in the center is because there might be some dirt particles inside the liquid. Okay? And if the liquid in the middle is undercooled, then you will stimulate nucleation of grains inside the liquid ahead of this interface. Okay? So you have to have some sort of dirt particle, because to get homogeneous nucleation is incredibly difficult. You require huge undercoolings. Okay? So first of all, you must have some dirt particles, and secondly, the liquid here must be below the fusion temperature. Now, how can that happen? Well, there are two scenarios. This is the normal scenario, where because we are withdrawing heat from the mold, okay, so this is hot, this is cold, and heat flow is in this direction. There will be a temperature gradient. The liquid away from the mold will be hot. As you get towards the solid-liquid interface, this will be about the fusion temperature, and then you're withdrawing heat from the solid and dissipating it into the surface. That's the normal scenario. But it's possible that you generate a lot of heat at the solid-liquid interface, because that's the enthalpy of fusion. Okay? Now, if you're generating a lot of heat at the solid-liquid interface, then the temperature here might actually be higher than the temperature further away in the liquid. Okay? In that case, this liquid here, you will get some nucleation on dirt particles. Okay? Now, this is a scenario which actually makes this interface unstable. Okay? Because supposing I put a small perturbation on this interface. So by a perturbation, I mean this is our interface here. And just by pure chance, it tends to develop a small perturbation. Okay? Because remember, this is a dynamic process. Atoms are moving in both directions and so on. So there's a chance that the interface won't be perfectly flat. If that happens, then that is actually going into colder liquid. So it will grow faster. And that perturbation will become unstable. Okay? In other words, what was a nice and smooth interface will tend to develop features like this. Okay? So the interface becomes unstable if the liquid ahead of the solid-liquid interface is undercooled. Okay? Is everyone happy with that concept? Yeah? If I go back to this point, there's no way that this interface would be unstable, because if I put a perturbation on it, it would advance into hotter liquid. Okay? But here, it's actually advancing into colder liquid. And therefore, solidification is favored, and it will tend to grow. The perturbation will tend to grow. So instead of getting smooth solidification with either a planar interface or a sphere, we tend to develop extremely convoluted surfaces. And these are called dendrites, because in 3 dimensions, they appear like trees. Dendros in Greek stands for trees. And here, for example, is a real picture of a dendrite. And this is a dendrite of ice that is forming in water. course, this is we are discussing pure systems at the moment, and water is water. And this is a dendrite of ice that is growing in water. It's really quite beautiful in 3 dimensions. There's a whole book published called Snow and Ice Crystals with incredibly beautiful pictures of dendrites. Of course, the perturbation, you see, this is a case where we are below the fusion temperature. But I could start with ice and warm it up, and I should get dendrites of water inside the ice. Okay, so this is a case where these are actually dendrites of water which are forming inside solid ice as the ice tends to melt. Now, can anybody tell me why we have these holes in the middle of every single dendrite of water? Volume change, that's right. So this is a system where the ice has a lower density than water. So when the dendrite of water forms, you must have a volume contraction, and it leaves a hole inside each dendrite of ice. You can even form these dendrites from the vapor phase. So here, I happen to be in a region of China called Harbin in January, where the temperature was minus 25 degrees centigrade. Okay, so you get this frost forming on the windows, and you can see these beautiful dendrites of ice forming from the vapor phase on the windows. Okay. So dendrites are extremely common in all solidification processes, but remember that this is a very special scenario where we have to have, in the case of a pure substance, we have to have this negative temperature gradient in the liquid to get dendritic solidification. If this is the case, then we will get planar solidification. Okay? And of course, we deal with a lot of pure materials, but the vast majority of materials that we deal with contain many different elements. They are deliberately added to control the structure and properties. So we'll come to that next. Okay, so now let's look at a system which has 2 elements in it, a binary alloy. Okay, so I'm going to introduce you now to the terminology. So this is our phase diagram. We are plotting temperature against the concentration of a solute. And it's a very simple phase diagram. Here, the liquid is stable. Below this line, we have only solid stable. And this is the 2-phase field in which solid and liquid are the stable phases. Okay, they exist in equilibrium. And C0 represents the composition of my alloy, the average composition of my alloy. For example, I might have 40 atomic % of zinc in copper. Okay, so C0 in that case would be 40 atomic %. The terminology I use here and here represents the equilibrium composition of solid, which is in equilibrium with liquid, and this is the equilibrium composition of liquid, which is in equilibrium with solid. Okay? So if I have my alloy at this temperature, then the equilibrium composition of the solid is this, and the equilibrium composition of the liquid is that. Okay? So the terminology here means that this is the concentration of solute in solid, which is in equilibrium with liquid. So you can't talk about the equilibrium composition of a solid in isolation. You have to say that it's the equilibrium composition when it's in contact with something else. Okay? So do you remember that this is called a tie line of a phase diagram? Okay? So it just connects the equilibrium compositions of the 2 phases. So as I take my material from liquid and I cool it, at any given temperature, I have the phase diagram giving me the composition of the solid that forms and the composition of the liquid that forms. If I cool further, then the composition of the solid moves down this phase boundary and that of the liquid down this phase boundary. And a very large number of phase diagrams, these lines are more or less straight lines. Okay? So we can define something called a partition coefficient. That means partitioning of solute between liquid and solid, which is simply the composition of the solid in equilibrium with liquid divided by that of liquid in equilibrium with solid. Okay? So the whole of this phase diagram we could express in terms of a single partition coefficient, given that these are just straight lines. Okay? Okay. So since I have this relationship, I can replace this term here, the CLS, by simply CSL upon K. Yeah? So I haven't done anything clever here, simply replaced this here by this term here. And when you look at the distribution of solute at the solid-liquid interface, it will then look like this. So at this particular point in the solidification process, this is the composition of the solid phase, this is the composition of the liquid phase, and far away from the interface, we still have the average concentration. Okay? Now, this is increasing in the solid. The solid is not homogeneous because we started solidification at this temperature. And at that temperature, the equilibrium composition of the solid was small, and it increases as solidification proceeds. Yeah? Is everybody happy with the fact that this should rise as I go down in temperature? Yeah? Simply because we started solidification at this temperature, and the composition of the solid moves along that phase boundary as we cool. Okay? So here is our bar, which is solidifying. At any point, at any given temperature in the solidification process, the tie line defines the compositions at the interface, and the far field composition is C naught. Okay? So we're assuming that it extends a long distance. Okay? Now, you will get to a point where this composition C naught intersects this phase boundary. Okay? That means that the composition of the solid becomes equal to C naught. And at that point, you will no longer partition solute in the liquid because the equilibrium composition of the solid is C naught. Okay? So as I cool my system further, this line here will eventually intersect this line, and CSL becomes C naught, and I no longer partition solute into the liquid. The only reason why we have a buildup of solute in the liquid ahead of the interface is because these two are different. The solid has less solute than C naught. Okay? Once the solid composition becomes C naught, there's no longer any partitioning of solute needed. Okay? So you will, at some stage, get to a point where the equilibrium composition of the solid is the same as C naught. Okay? And then the amount of solute in the region ahead of the liquid remains constant. And we call this situation steady state solidification, because now, even though there's diffusion happening, it's happening at a constant rate because we are not dumping any more solute into the liquid. Okay? So at the point where CSL becomes equal to C naught, we have steady state solidification. So at that point, the interface moves with a constant velocity. Okay? Can you remember another steady state scenario that we considered in an earlier lecture? Where we had diffusion happening, and yet nothing was changing in the concentration profile. Yeah? Do you remember the Fick's first law scenario? Where we had a sample of material with a constant concentration here and a constant concentration here, and diffusion happening in that direction. Okay? So if you were an observer located here, you would see no change, okay, because these points are not changing. And yet, you are dissipating free energy because diffusion is happening. Once we reach steady state solidification, the same applies. If you are an observer located on this interface as it moves, then you will see no change in the profile ahead of the interface because the concentration of solute in the solid is C naught. Okay? And that's the scenario that we will look at. We will not look at the transient as it builds up to steady state solidification. So that simplifies things considerably, because at the point where we have steady state solidification, this is equal to this, and we can, if I'm an observer located at this point, I will see no change as the interface moves. Now, we've got to derive an equation describing this scenario. There are two terms in this equation, okay? And I'll illustrate those terms to you. You can see that as this solid phase grows, and I've got to this point, okay? First of all, I've displaced the whole of this concentration profile with a velocity v, okay? So at any point over here, there is a change in concentration simply because the whole of that concentration profile is being displaced. And that is this, okay? The rate at which we displace that concentration profile is velocity times the gradient over there, okay? So there's a change in concentration over here simply because the profile is being displaced with a velocity v, okay? So this is the new position of the profile, and the concentration has changed from here to here. And that change is given, the rate of change is given by the velocity times the gradient. And the second thing is that, of course, we have diffusion happening down this gradient, okay? So that is given by Fick's second law, because this is not a constant gradient. Now, these two terms must be equal, since the shape of this profile is not changing as the interface moves. So just to repeat, there are two terms here which have to balance each other if the shape of the profile is to remain constant. The first is that as the interface moves, the whole of the profile is being displaced. And the second is that you've got diffusion happening, given by Fick's second law, because this is not a constant gradient. And these two terms must balance, and therefore that must equal 0. Okay? Everyone happy with that? Yeah, so this is the basic equation that we have to solve to derive the velocity as a function of all the other terms. Okay. Now, the second thing that we need to look at is a sort of a mass balance condition, that this area here is the amount of solute that has been pushed by the interface. If I multiply that by the velocity, I get the rate at which solute is being pushed by the interface. Okay? You know, when the profile moves from this point to this point, I've displaced that much solute. I've exaggerated the distance between these two. If I make it very small, then you see that it's the difference between the concentration here, multiplied by the velocity. Okay? That's the amount, the rate at which solute is being pushed ahead of the interface. And that solute has to be carried by diffusion at this point. Okay? So this is the gradient at this point at x equals 0. So these two terms must be equal if I'm going to maintain the concentrations at these 2 points constant. Okay? So we have two equations. One really examining the concentration at a point here and balancing the fact that the whole profile is moving with, at any point ahead of the interface, diffusion driven by Fick's second law. Okay? And the second is a kind of a mass balance condition that, you know, I'm pushing this much solute ahead of the interface, and that has to be carried away by diffusion. And the gradient at this point is, at x equals 0, carries that solute away by diffusion. And if these two terms are equal, then this point remains constant. Okay? So we have two equations, and we can solve the velocity. So here are the two equations. If I integrate this equation, I will end up with this, subject to this as a boundary condition. So let me go through that integration. I emphasize that you don't need to remember this, okay? This equation is given to you in your data book here, this particular equation, but it's nice to understand where the equation comes from, okay? So you've got here a diffusion coefficient and the second derivative of concentration with respect to x, and the first derivative. So I'm going to call this term here y, in which case this becomes dy by dx, right? So here, I've just rewritten that equation which had a second derivative here as dy by dx and v times y. Okay? Is everybody happy with that substitution? Yeah. So I can then rearrange this equation as dy over y is equal to minus v over d into dx. Okay, that's just a rearrangement from here. And that immediately suggests that, if I integrate this, I will get logarithm of y here. And of course, there's an integration constant. Yeah, so if I integrate this equation, I get logarithm of y here because, differential of logarithm of y is dy over y. Integral of x is x, dx is x, and this is an integration constant. And that integration constant I can solve for using, I'll come back to this slide, okay, using this condition here, because I know that at x equals 0, the gradient is given by this divided by minus d, okay? So to solve that integration constant, I use that equation for the gradient, the value of the gradient at x equals 0, and I get my integration constant as log y naught, take it onto this side, and I have this equation here. Okay, so to get to this stage is fairly straightforward. All we did was we substituted dc by dx by y so that we can simplify this equation. We then integrated, there was an integration constant, and we used the fact that we know the gradient at x equals 0 to solve for this integration constant. And now I take the log y naught term over here, and I get this is equal to this. Okay, now if I take the antilog of that, then I get the term in brackets here, an exponential of minus vx upon d. And then I substitute for y as dc by dx, and I get this equation here. And therefore, I have my final equation here, which once again you integrate to get the equation I illustrated in the previous slide. Okay. Now, I'm actually making all the slide presentation available on the website, so you can have a look at this again if you want. But if you carry out that final integration, you get this equation, which tells you that the concentration varies exponentially ahead of the solid-liquid interface. And the details of that variation depend on the diffusion coefficient of the solute in the liquid, the velocity of the interface, and the distance ahead of the interface. Okay? This part is really trivial because we are simply using the partition coefficient to replace these terms. Okay? Is everybody happy with that? So for the case where we have solute diffusing ahead of the interface, you've seen that the interface velocity is more complicated, and that's reasonable because not only has the interface got to move with the transfer of atoms across the boundary, but you've also got to diffuse solute because the composition of the solid is not the same as the composition of the liquid. And therefore, you get a concentration profile ahead of the interface. And under steady state solidification, that means at the point where the solid composition, the equilibrium composition of the solid is C0, the velocity of the interface is given by this equation. Okay? This actually describes the concentration profile ahead of the interface, but you can rearrange it to express it as the velocity as a function of the phase diagram, and these are quantities from the phase diagram. Okay? Now, the reason why I dealt with steady state solidification is that when we are away from steady state, that means when the composition of the solid is not equal to C0, all the boundary conditions are changing during the solidification process. You know, the equilibrium compositions of the solid and the liquid are changing. That is a much more complicated problem to treat. It can be done, and it is done, but it's not worth doing in this lecture course. Okay? But the methods all exist for doing such calculations. And notice also that I'm dealing only with binary alloys. Yeah, so we have only one solute. A real material might contain a dozen solids deliberately added to control the properties. So we have to think about multi-component diffusion and how one solute species keeps pace with another solute species, because there's only one interface moving. Okay? And we've also made the assumption that there is equilibrium at the solid-liquid interface. We've said that the compositions at the solid-liquid interface here and here are given by a tie line of the phase diagram. There are many solidification processes where we force solidification to happen rapidly, and then that will no longer be the case. So we have to deal with non-equilibrium solidification as well. Okay? So this lecture today is an introduction to solidification theory, and you should realize the approximations that I've made in deriving this equation. First of all, I've assumed steady state solidification. Okay? So these are the assumptions. Okay. Steady state solidification. We have equilibrium at the solid-liquid interface. Interface. That we are dealing with a binary alloy. So these are important assumptions. And although this equation will be valid for many scenarios, it will not be valid for most real materials where we have many, many different solutes, and solidification may not be steady state, and the solidification rates that we force on materials might be so large that you will get deviations from equilibrium. Now, there's one more slide that I want to show you. And that is, you know, when I draw pictures of dendrites and when I showed you the pictures of ice and so forth, the interfaces of the dendrite looked very smooth. Okay? But crystallography also comes into play. This is a dendrite of niobium carbide. Okay? And you can see it is highly faceted, because in this case, the interface energy is strongly dependent on the orientation of the interface. So these, for example, are the 100 planes of the dendrite. And this dendrite grows rapidly along the 100 directions. This is what I was telling you earlier, that in cubic systems, systems with lattices which are cubic, the fastest growth direction is 100. Do you have any questions? Okay, so have a look at the lecture notes. If you have any questions, come back when we begin on Thursday.